Let's continue with the previous video. How this connects to what we were talking about before. Earlier we discussed CIDR, subnets, and mask. Broadcast addresses like 10.0.0.1274/25. How IP map to Ethernet MAC. Now the book is moving from broadcast to multicast because broadcasting is wasteful, but inherently it actually uses still broadcasting, but within the subscribe parameters. Why multicast exists? Because broadcasting sends traffic to all devices in the network. Example, our broadcast go to every host on the LAN. Every host has to process them, even if they don't care. This is inefficient because, especially on big networks. Multicast fixes this. Only hosts that want the traffic receive it. So, broadcast who receives it, everyone. Multicast, only listeners who join the group. How multicast works in IP? In IP networks, a device that wants to receive a multicast stream joins a multicast group. That group is identified by a multicast IP address. As we will later see, it could be a multiple IP or multicast IP address in that one multicast group. Example, in IPv4, 224.0.251 is mapped to MDNS multicast group. Devices that support MDNS subscribe to this address. So if you want to support that in your OS, you need to send the multicast to this 224.0.251 to be able to subscribe and receive any host that also subscribe to that. And you will actually see that in Wireshark. Then when someone sends a packet to 224.0.0.251, only subscribers receive it. How does this relate to MAC addresses? Remember, Ethernet frames need a MAC destination address. So when sending to a multicast IP, it must be translated into a multicast MAC. IPv4 mapping. IANA owns the Ethernet prefix 01:00:5E. So multicast MACs looks like this: 01:00:5E:XX:XX:XX depending on the available. But IPv4 multicast IP has two 28 usable bits. MAC mapping only stores 23 bits, meaning 32 different IPv4 multicast IPs can map to one Ethernet MAC. So, a 32 multicast IPv4 IP can actually be mapped to just one interface. This is called far-in mapping or aliasing. IPv6 multicast MAC mapping. For IPv6, MAC prefix is 33:33. Last 32 bits of the IPv6 multicast address are copied directly into the MAC. Example mapping: IPv6 to FF02::FB, MAC to 33:33:00:00:00:FB. Why is IPv6 linked local in these examples? When you see something like FE 80:208:74 FF::FE93 C8 C83C, that is a linked local unicast IPv6 address, and most of multicast is actually within the LAN or linked local, meaning valid only within the LAN, not routed outside. In multicast ping examples, ping 6 uses a linked local address because Multiple groups like FF02 colon FB have local scope. 02 indicates link local scope. Local multicast must originate from a local link address. So the FF02 is within the LAN. So a local multicast must also originate within the LAN. How this connects to previous conversation like CIDR and broadcast, all are part of the same layered networking rules. CIDR and subnet mask determine which range of IPs belong to a local network. So these are just a way to allocate. It doesn't mean anything. It's just a way for you to determine which range of IPs belong to a local network. Second, broadcast addresses send all hosts in that subnet. For example, 10.0.0/25, the 10.0.0.127 is broadcast. Multicast, instead of sending to everyone, send only to devices interested in a given service. Fourth, MAC mapping, routers and NICs must translate IP to Ethernet address because Ethernet actually carries the frame. Real world example you can see on Linux, IP space MADDR shows which multicast MACs a NIC is listening to, or ping an MDNS IPv4 multicast group, ping 224.0.0.251, or IPv6 example, ping 6 space dash capital I space ETH0 space FF02 colon FB. Only devices that join the group will reply. Summary in one page. Broadcast sends traffic to everyone. Multicast sends traffic only to group members. In IP, multicast groups are identified by special IP ranges. IPv4 224.0.0.0 to 239.255.255.255.255. In IPv6, that's FF00 colon/8. These IPs must be translated into multicast MAC addresses. IPv4 uses 01:00:5E plus last 23 bits. So that's how it map or convert that multicast IP address allocated for multicast IPv4. And for IPv6, it uses a MAC address 33:33 and last 32 bits, which is actually easier to convert. IPv6 link local addresses appear because many multicast scopes are linked local. So that's the reason why you have IPv6 link local address, because most of the multicast is actually within the LAN. So how does it connect back to the cloud? How do you subscribe to a multicast group like MDNS on your laptop at home? Short answer, you usually don't do anything. Apps automatically subscribe. Examples, apps that automatically join multicast groups without you knowing. Application, Windows or Mac OS or Linux. Networking, join multicast group. It joins FF:02:1 all nodes and FF02:2 all routers. Why? Required for IPv6. So that's on the networking part of their application. Chromecast join multicast group. Yes, it joins 224.0.0.251. Why? To advertise itself to those that subscribe to those to be able to use it. Apple Bonjour joins 224.0.0.251. Why? To discover printers or devices. Zoom or Teams sometimes joins multicast for. So does it join multicast group? It joins multicast for discovery. Why? For enterprise use. DLNA Smart TV, is it joining multicast group? Yes, it joins multicast. Why? Device discovery. Your laptop and router subscribe to multicast groups automatically when needed. You can see this yourself. In Linux, IP space MADDR, Mac OS netstat space -G, Windows netsh space interface space IPv6 space show space joins. If you run those, you will see your system already joined multicast groups like FF02 colon 1, FF02 colon 2, 224.0.0.251. So the OS, the application, and its network stack automatically join. Why does IPv6 link local appear in multicast like FF02 colon FB? Because IPv6 multicast scopes define how far a packet can travel. Scope values FF02 colon/16 meaning link local only, LAN only. For FF05 colon/16 meaning site local. FF0E colon/16 meaning internet or global. So FF02 colon FB is a multicast group FF with scope equal link local 02. That means it must be sent using a link local source address because it cannot leave the LAN. So when you ping 6 space FF02 colon FB, you see your system use something like FE80 colon ABCD colon 1234 colon 5678. That is its IPv6 link local address generated automatically from the NIC MAC address. Third, how are link local addresses created? IPv6 automatically generates them. FE80 colon plus interface identifier. So aside from automatically joining that multicast address, the IPv6 stack actually automatically generates them, and for IPv6 is actually faster because it just needs FE80 colon plus interface identifier. Examples: FE80 colon ABCD colon 1234 colon 5678, then FE80 colon 1, then FE80 colon 208 colon 74FF colon FE93 colon C83C. Every IPv6 interface must have one. They are not assigned by DHCP, ISP, router, or cloud. They exist the moment the OS enables the NIC, even without a router, even without the internet. So this FE80 plus interface identifier actually doesn't need a router or the internet. The OS, the only thing that needs here is the OS and the NIC to be able to combine this FE80 colon plus interface identifier. What is a subnet mask really doing? 10.0.0.0/25 means part 10.0.0.0 meaning the network prefix /25 first 25 bits belong to the network, remaining 7 bits host addresses. The MAX decides which IPs are considered local, which ones must be sent to the router gateway, example device, IP colon 10.0.0.13, mask colon /25 to 255.255.255.128, range colon 10.0.0.0 to 10.0.0.127. If the device tries to send 10.0.0.66, that's local, no router needed, then 10.0.0.200 outside subnet, sent to router, just basic math on bits. How does this relate to AWS or Azure or GCP? In cloud, VPC or subnet, you assign CIDRs like 10.0.0/16, 10.0.1.0/24, 10.0.2.0/24. They represent private networks inside the cloud, used for EC2 instances or Azure VMs. So this CIDR, the /16/24/24, or the 10.0.1.0/24 and 10.0.2.0/24 are just a way for you to allocate it within your network. Now they represent private networks, so it will allows you to provide as much host or as much configuration in network and host as you would as it possible to do. They represent private networks inside the cloud. It's used for EC2 instances or Azure VMs. Kubernetes nodes, app service backends, database. Private CIDRs allow internal communication with no public internet. Routing without NAT. Security isolation. Public IPs only assigned to load balancers, not gateways or a single VM if exposed. So those are the private, that's the difference between the assignment of private IP and public IP. Because public IP is only assigned to load balancers, not gateways or a single VM. So inside the VPC or subnet, it communicates using private IP. No public internet needed. Outside of the internet, requires NAT or public IP. Do things inside the same VNet need IP? Yes. Even two containers on the same server need IPs or unique sockets. Because again, this IP plus port connection is how you create the socket for each one of them. Networking always routes using IP plus port, even when traffic never leaves the machine. How is multicast MAC address mapping done? Kernel detail. For IPv4, all multicast IP addresses 224.0.0.0 to 239.255.255.255 are mapped to MAC address starting with 01:00:5e::xx::xx::xx. Example 224.0.0.251.201:00:5e::00:fb. Mapping rules. OS kernel extracts lower 23 bits of the IP, inserts into 01:00:5e::xx::xx::xx. For IPv6, multicast always maps to 33:33:xx::xx::xx::xx::xx. Example FF02::FB to 33:33:00:00:00:FB. Where is this stored? Inside the OS kernel networking stack. When a socket joins a multicast group, the kernel first adds the MAC address to NIC filtering table. That's how you see the routing table that we discussed in the previous and what we will also discuss in the future videos. Second, NIC starts accepting Ethernet frames whose destination MAC matches the multicast group. So the OS kind of like configuring or programming the NIC to be able to accept on that by having it saved on NIC filtering table. This is also the complexity of multicast in which it needs to configure the state dynamically based on who joins and where it joins. This is not burned in the factory. The NIC supports unicast, broadcast, multiple multicast address, but the specific multicast addresses are programmed by the kernel at runtime. So why do many IP multicast address map to a few MAC addresses? Because IPv4 has 228 possible multicast addresses, but only 223 possible MAC addresses for IPv4 multicast. So as you can see, you have a distinct number for MAC addresses, for its MAC addresses, and its layer 3 address. So 32 multicast IP groups share the same MAC. NIC receives them all. Kernel filters further using IP headers. So if you want to filter that further, you're gonna go upwards from IP layer to the transport layer. This is a trade-off to avoid needing ARP for multicast. So this is another trade-off aside from keeping with the state, is that you'll have to deal with security on the upper layer. Putting it all together in one sentence, your OS automatically joins multicast groups, programs the NIC to listen for the corresponding multicast MAC addresses, and delivers packet only to applications that requested them. Even at home on Wi-Fi, because multicast is part of everyday local networking, MDNS, service discovery, routing protocols, IPv6 neighbor discovery, etc. So here is my interfaces. So I have Wi-Fi, I have Memo switch, Ethernet 2, local area connection 11 and 12. So what it means, so every IPv6 device automatically joins certain multicast addresses, so it can participate in IPv4 network operations, network discovery, MDNS, DHCPv6, etc. Each row shows interface, the network adapter, Wi-Fi, Ethernet, virtual adapters, etc. Multicast address, the group the interface joined, references, number of processes using it, last, whether it has been active recently. Why this happens relating to the earlier discussion about networking. In our previous networking discussion, we were learning how IPv6 works on Windows, how bridges and interfaces learn addresses, how Wireshark or diagnostic tools show MAC and IPv6 tables, how your PC participates in a network traffic. This output fits directly into that topic. IPv6 multicast is replacing broadcast. Unlike IPv4, IPv6 does not use broadcast at all. Instead, device join multicast groups like for multicast FF02::1, meaning all nodes on local network. For multicast FF02::C, meaning SSDP used by discovery services. FF02::FB, MDNS used by device name discovery. FF02::1:FFXX::XXXX, solicited node address like ARP in IPv6. These groups are how devices discover neighbors, resolve MAC addresses NDP, announce services, detect routers, support shared software like VirtualBox, Memo, Hyper-V adapters. Why you see multiple interfaces? You have many interfaces: Wi-Fi, Ethernet, Hyper-V, virtual switches, Memo emulators, which look back, each one gets its own multicast subscriptions. Virtual adapters join this group too because they also run their own networking stack. Should you worry? No, this is normal IPv6 behavior, not an error. You would only be concerned if you saw strange multicast groups you didn't recognize and your PC was acting compromised. But nothing in this looks suspicious. One line summary: your PC is simply showing all IPv6 multicast groups. Each network interface has joined so that IPv6 networking features can function properly. This is expected and normal networking behavior. Now, sending multicast diagrams. How do we actually send that? When sending any IP packet, a decision must be made as to which source address and interface to use. This is especially true for IPv6, where having multiple address per interface is considered normal, because again IPv6 is abundance in its available IP. Also, this has been configured when sending, that's the first thing to be configured when sending a datagram. To determine this, we can look at the forwarding table present in the host. In either Linux or Windows, the netstat command can be used. Here are the IPv4 and IPv6 routing table as output in Windows Vista. So these are important command, netstat-rn, because this is actually how our PC keeps the state. Remember, they automatically subscribe to the needed multicast addresses. They also have this, or you are also allowed to see what interfaces are available and to where they are connected. From this table, we can see that a default route for IPv4 traffic goes to 10.0.0.1 using interface 10.0.0.57. So that's the default because it has the lowest metric. So your system will gonna use this because it has the lowest metric by default, unless otherwise specified. Although this does not match multicast traffic, there are other entries that are more specific. The entries listed as 224.0.0/4 subnet mask 240.0.0.0.0 indicate that three different interfaces can carry outgoing multicast traffic. So as we can see here in 224, it has different interface and they can carry a multicast traffic. So these are normal for a router, but these are not normal for a laptop or like a user PC. The interface with the lowest Mach 10.0.0.57 with metric 281 is the most preferred, so it is used unless an application in the upper layer specifies otherwise. For IPv6, all multicast addresses begin with FF and there are no broadcast addresses. So interface 1, 9, and 10 can all be used. So again, there's no broadcast in IPv6 because that's not allowed for them. And it begins with FF. So 1, 9, and 10 can all be used. Interface 9, which happens to be the same interface used for IPv4, and the default for IPv6 unicast traffic has the lowest metric. So the interface 9 has the lowest metric and also happens to be the same interface used for IPv4. Additional information indicating which interfaces have which IP addresses can be determined using the Windows command ipconfig/all. So additional information indicating which interfaces have which IP in this IPv6 routing table can be seen using ipconfig/all, not netstat-rn. The output on Linux is separate for different protocol families such as IPv4 and IPv6. Unlike in Windows, it isn't they are in one screen. It is generated by different arguments to the netstat command to indicate which version of IP or other protocol is of interest. For IPv4, there is nothing to show as there is no special entry for multicast. A conventional default route handles the multicast traffic. For IPv6, however, we can see the following: netstat-rn-A enet6. So as we can see, kernel IPv6 routing table, destination ff00::/8, next hop ::, u metric 256 rev 0, use u iface eth 0. In this case, there's no direct next hop. That's why : so the unspecified : is listed in the table. But we can see that the outgoing interface is eth0. The flags column contains only u, indicating that the route is usable, but the lack of a G indicates that it is an on-link route, not requiring forwarding to a router. So let's answer a lot of questions and confusions here. So first, what are we looking at? The output we pasted netstat-rn and the IPv6 joins show how laptop decides. So first, which NIC or interface to use, which IP source address to use. Third, how multicast packets are sent. Fourth, which multicast groups your host is subscribed to. This makes sense only if we understand one thing first. A computer can have multiple network interfaces or NIC and multiple IPs. So the OS needs routing rules to decide which interface is used to send a packet, when and where and which. And it actually changes dynamically. That's why the OS needs some memory or routing table for that. Multicast makes this more complex because you are not sending to a normal unicast IP. There may be multiple NICs capable of sending multicast. IPv6 interfaces have multiple IPs. Why you never saw this before? Because normal home networking is too simple. You have one NIC Wi-Fi, one default route, all traffic just goes through that. So you never saw a situation where multiple interfaces can send multicast. Multiple route entries apply. Multiple IPs exist on the same interface. Now, you're reading material written for servers and routers, where this complexity is normal. So multiple route entries could also be applied. Like you could have multiple interface, multiple IP, all are connected at the same time. What does the routing table mean? Example from our screenshot: 224.0.0, 224.0.0 on link to 10.0.57 metric 281. This means any multicast IPv4 address 224.xxx to 239xxx can be sent directly through interface IP with IP 10.0.0.57. So any multicast IPv4 that has those or sending those could be sent directly through this interface or through this NIC. So anyone that is subscribed to this IPv4 could send their datagram through this NIC. Metric 281 equals priority, lower equals better, meaning it will be prioritized by the OS. But there were 3 entries as well: on link 127.x.x.x, and then on link 169.254.x.x. On link 10.x.x.x. So this computer has 3 interfaces capable of multicasting. Therefore, the OS needs to choose one. It chooses the interface with the lowest metric. Here, that is 10.0.57. That's all the explanation. Second, why does multicast look different? Multicast is not like unicast. Feature, destination, unicast, one host. Multicast, many hosts. Feature, send method, unicast via router or default route. For multicast, usually on link broadcast to many NICs. Feature, routing entries exist, unicast, yes. Multicast, usually one shared range 224/4. So when the OS sees destination 224.x.x.x, it matches 224.0.0.0/4 and then decide which NIC should send it. Third, IPv6 is more complex. IPv6 allow many addresses per interfaces. Link local, FE80 :xxxx, global 2001 :xxxx, SLAAC, temporary privacy addresses, multicast addresses. So when IPv6 sends a packet, it needs rules to decide which source address and which interfaces to use. Thus, you see multiple routing entries. So that's also how the OS choose which source address, and how we discussed earlier that the multicast has a problem of choosing which source address when sending and which interfaces to use. Thus, you see multiple routing entries. But it answers a little bit by having the OS choose the lowest metric. FF0 :/8 on link interface 9, FF00 :/8 on link interface 10. Meaning any IPv6 multicast FF00 :/8 may go out multiple NICs unless something chooses one. That something is route metric, application selection, OS policy. Fourth, what about your NetSH interface IPv6 show joins output? You saw entries like FF02 : FF02 : FB, FF02 : C, FF02 : 1 FFCA :E71A. This is which multicast groups your laptop is currently subscribed to. Later we will see my laptop current subscribe interface. Example address: FF02 : 1 purpose all IPv6 nodes, FF02 : FB purpose MDNS multicast DNS like .local discovery on Windows or Apple, FF02 : C purpose SSDP / UPnP service discovery. Examples: FF02 : 1 FFXX XXXX purpose neighbor discovery, ARP replacement. So your computer is automatically listening for printers, file sharers, Chromecast, smart TVs, other local services. You did not configure this manually. Devices automatically join local link multicast group at boot. Is multicast only local? Yes, here's why. IPv6 FF02::/16 equal link local multicast, meaning valid only inside the LAN. Routers must not forward this. Same in IPv4 224.0.0.0 to 224.0.0.255 is local control only, never forwarded beyond the network. So, your multicast DNS to FF02::FB is only seen inside your home network. That's why you can discover a printer automatically, but someone on different subnet cannot. How does multicast map to MAC addresses? This part confuses you, so here's the missing link. Ethernet must deliver to a MAC address, but multicast IPv6 is to FF02::FB. How do we know what MAC to send to? Answer, there's a deterministic mapping defined in standards. IPv4 mapping, take IPv4 multicast 224.x.x.x, convert last 23 bits into 01:00:SE:XX:XX:XX. IPv6 mapping, IPv6 multicast FFXX: it maps to 33:33:XX:XX:XX:XX. So NICs automatically filter multicast with unicast MAC, your hardware address, broadcast MAC 6FF, and certain multicast MACs derived from IP. This is done in the NIC hardware plus OS driver. It is not burned at a factory. It is calculated dynamically, and it changes states dynamically depending on your application subscribe multicast. So we didn't understand this because until now we only thought of IP routing, but routing decides NIC first. Ethernet still needs a destination MAC. NIC hardware must filter frames. OS must map IP multicast, MAC multicast. Multiple NICs must choose precedence. IPv6 often has many addresses per interface. We were missing the layer 2 plus layer 3 plus OS linkage. Now you see, multicast is not magically broadcast. It is sent to special MAC addresses. NICs subscribe to multicast groups. OS routing chooses which NIC sends. IPv6 has complexity due to multiple addresses. Final summary, the missing explanation. When your computer sends a multicast packet, first, OS looks up routing table to decide which interface or NIC is preferred, lowest metric wins. Second, OS determines which source IP on that NIC to use. Third, OS converts multicast IP to a multicast MAC. Fourth, NIC sends Ethernet frames to 01:00:5E:XX:XX:XX for multicast IPv4, 33:33:XX and then XX for multicast IPv6 MAC address. Fifth, other NICs on the LAN receive it and their hardware checks if they're subscribed. If yes, passed to OS. If not, discarded in hardware. Your netstat-rn and netsh IPv6 show joint output shows which NICs can send multicast, which multicast groups your OS is listening to. So first, what are we actually seeing? When you run netstat-rn, Windows shows first all network interfaces on your machine. Second, all multicast routes that each interface can use. So if you see 224.0.0.0, 224.0.0.0 on link 192.168.1.47, and then the same 224 and 240 on link 417.2.17.144.1, and then the last is 127.0.0.1. This means Windows has 3 NICs that are up. So Windows automatically adds a multicast route 224/4 to each of them. That matches the book statement. Multicast traffic can be sent out multiple interfaces. The lowest metric interface is chosen unless the app specifies otherwise. Which interface actually gets used, even though all three are available, like 192.161.14.7, meaning your Wi-Fi converged router, used, yes, in real LAN multicast. Interface 172.17.144.1, meaning Hyper-V virtual switch, is it used? Only used by virtual machines. 127.0.1, meaning loopback, is it used? Only used inside Windows itself. This is exactly what the book means when it says a default route handles multicast unless another route is more specific, because normal multicast apps, Chromecast, printers, smart TVs, SSDV, MDNS, etc. are running on your real network. They will use 192.168.1.x. Where does metric fit in? The OS must pick one interface to send multicast out if multiple are valid. So it checks metric, lower metric equal higher priority. If 192.168.1.47 has metric 291 and 172.17.144.1 has metric 305, the Windows chooses Wi-Fi 192.168.1.47 by default. This is what the book meant. The interface with the lowest metric is preferred. So how does this relate to your daily life? Real multicast, you actually used your Wi-Fi interface 192.168.1.x handles discovery and streaming for smart TVs, Chromecast, printers, window file sharing, AirPlay, NDI or OBS, smart home devices, SSDP/UPnP, MDNS, .local, game streaming, all those use multicast only inside your LAN, not over the internet. Why does Windows show Hyper-V there? Because Hyper-V is a software switch, so Windows treat it like another NIC, even if nothing is using it. Windows still says, well, if a virtual machine wants to send multicast, this is the route. So 172.17.144.1 is not used by Chromecast. It is not used for local LAN tools. It's only used if you run Hyper-V virtual machines, WSL2, Docker desktop, Android emulators in Hyper-V mode. Otherwise, that entry just sits there harmlessly. How this ties perfectly to the book explanation? Let's map it to case that we quoted. Book said multiple interfaces can carry multicast traffic. You saw Wi-Fi, Hyper-V, switch, loopback. That exactly matches that statement. The book said route with lowest metric is selected unless app overrides. In your case, Wi-Fi has the lowest metric, so it is chosen. That is why all real multicast goes through Wi-Fi. Book said 224.0.0.0/4 shows which interfaces support multicast. You saw 3224/4 entries, meaning 3 NICs are capable. Not all are used in practice. The book said multicast routing must decide which source address and interface to use. Windows must choose which NIC to send from, which IP on that NIC to use. So the routing table is the OS way of making that decision. Book demo Linux FF00::0 space capital U space ETH0, same idea, different OS. Final simplified explanation: why you see 3 multicast routes? Because you have 3 active network interfaces. Why only one matters? Only the Wi-Fi interface actually connects to converged LAN. Why this wasn't obvious before? Until now, you never examined layer 3 routing, layer 2 multicast mapping, multi-interface routing logic. Home networks hide all this complexity. How this relate to daily life? Every time you saw stream to a TV, discover printers, use that local addresses, use UPnP, do AirPlay or NDI, your laptop sends multicast via 192.168.1.x, not via Hyper-V or loopback. IPv4 multicast class D. When your laptop sends multicast to an IPv4 multicast IP such as 239.255.255.250 and 234.0.0.251, Windows or any host must convert that IP to a multicast MAC address so Ethernet can transmit it on the LAN. Formula: take the lower 23 bits of the IPv4 multicast address and map into 01:00:SE:(XX:XX:XX:XX). So always start with 01:00:SE. Higher bit of the next byte is always 0. Example, IPv4 multicast 239.255.255.250. Binary mapping produces 01:00:SE:7F:(FF:(FA). This is what gets placed in the Ethernet frame. IPv6 multicast. If the packet is IPv6 multicast, address starts with FF. The mapping rule is simple: 33:33 XX:XX:XX:XX. The last 32 bits of the IPv6 address becomes the last 4 bytes of the MAC. Example, IPv6 multicast capital FF 02::FB. FB becomes 33:33:00:00:00:FB. Where this happens in your stock: absence multicast socket right. Your Wi-Fi interface is chosen, lowest metric. Second, IP layer forms packet. IPv4 address equal IE 239.255.255.250. And it could be TTL, IGMP group membership, etc. Third, OS looks up routing table, decide which NIC to use, applies output interface address 192.168.1.x. Fourth, IP multicast address is converted to MAC. IPv4 01:00:SE:**. IPv6 33:33:**. Fifth, Ethernet frame is broadcast to the LAN. Switches deliver it only to ports that have hosts subscribe via IGMP/MLD snooping or FLAD if snooping is disabled. Inside the home network like Converge router, Windows sends multicast as Ethernet frames using those MACs. Your Wi-Fi router switches them locally. They never knew your home network TTL often equal 1. So smart TVs, printers, Chromecast, etc. can see them. Extra clarity: does multicast always need router involvement? On same LAN, no. Switching works at MAC level. Across different subnets, yes. Router must support IGMP, IPv4, PIM for inter-subnet routing, MLD for IPv6. Home routers usually do not forward multicast between subnets, which is why Chromecast won't work across VLANs. .local MDNS won't cross networks. Final summary: IPv4 multicast, destination IP: 224.0.0 to 239.255.255.255. Ethernet MAC: 01:00:SE: XX:XX:XX:XX. IPv6 multicast, destination IP: FF00::/8. Ethernet MAC: 33:33:XX:XX:XX:XX. Multicast gets sent out your primary LAN NIC. 192.168.1.x Wi-Fi, Hyper-V and local loopback also have entries but are not used unless needed.